This is a real pleasure. This is a real pleasure. Talk about a Renaissance type person. I made a little joke to him, and I'm just going to go ahead and tell you. So our speaker tonight, Jerry Campbell, is one of those rare people who, if he has a split personality and has a conversation with himself, can say, "Doctor, doctor." Okay, he has two terminal degrees. His first one, interestingly enough, was in relativity physics. And look at the title of that dissertation: Theoretical Study of the Distribution of Radiation, including gravitational radiation, from sources in proximity to the Milky Way galaxy supermassive black hole. Woo! What a topic. Okay. And then he decided, hey, physics is a nice hobby, but I want to do something significant with my life. So I'm going to get an MD degree. And so now he is the professor of neuropathology and autopsy, Department of Pathology at UTMB. But his presentation today is not on pathology, it's on gravitational astronomy. Now, interesting things on his medical research interest: the blood-brain barrier. I guess, like, how did nutrition get from the bloodstream into the brain? And I guess to follow up on that, cerebral small vessel disease. Very interesting stuff right there. National Science Foundation Fellow in Physics. I'm assuming that was to support your initial your PhD degree.
Yeah.
And then an MD lectureship for professionalism in medicine. Anything that has to do with professionalism, I think, is quite auspicious. And he is a member of the Johnson Space Center Astronomical Society. Without further ado, Jerry, I'll turn it over to you.
Thank you. Thank you very much for the invitation to talk to you all. Let me share my screen. Okay, make sure you can see that. And make sure you can hear me okay. I don't hear any negatives. So. Is that good? Okay, good.
Yeah.
Thank you. All right, so this is a topic that I've had a longstanding interest in, as you kind of gleaned, I guess, from the introduction. Let's see. There we go. So I have broken this up into different areas. I'm going to start out with some of the history of gravitational radiation and talk a little bit about my personal interest, then about some physics, how these gravitational waves are detected, and even though the physics is cool, it's the engineering that makes it possible. So if any of you are engineers, I think you can relate to that. What has been found and what it means for astrophysics and cosmology, and what's planned for the future. So these are the topics. So regarding the history, this background image is the Memorial Garden at the University of Maryland for Joseph Weber, who was one of the first people to try to detect gravitational waves. And actually, his work kind of led into my PhD project. My advisor had trained at the University of Maryland, and so he knew about Joseph Weber. And at the time, Weber was reporting some results that really seemed to be a lot of energy coming from the center of the galaxy, or at least that's what he presumed. And so much so that it was not really reasonable that that much energy would be radiated away. So my advisor's idea was, well, maybe this isn't isotropically radiating and it would be focused in the plane of the galaxy, and that would alter the amount of energy being calculated. And so that became my PhD project, to do a theoretical calculation for that, basically involving something like gravitational lensing of the radiation. Unfortunately, Weber's results came into question, and a lot of analysis suggested that he really wasn't observing what he purported to be observing, and the significance of our calculations, which were good, I sort of declined, as I should say. So I went to medical school. So let me talk a little bit about how people started to think about gravitational waves. Einstein really proposed them very early on in 1916 as he started to publish his work on general relativity. He was a little bit doubtful, but other people really placed that more in into certainty that general relativity did predict the existence of gravitational waves. So as I said, Joseph Weber was the first person really to attempt detection, but his results were further analyzed and not confirmed, although he never conceded that in his lifetime, I don't think. A really interesting indirect observation of gravitational waves was from the discovery of a binary pulsar by Hulse and Taylor in 1974. And I'll say a little bit more about that in the next slide. Obviously, as most of you know, the first direct confirmed detection by LIGO was in 2015. And then very soon after that, in 2017, there were 3 detector events determined, which really allows the localization of the sources to be much better. So the Hulse-Taylor pulsar is kind of interesting. It's a binary star system in Aquila, and it is a neutron star and a pulsar orbiting each other around their center of mass, and the radii of the orbit vary from about 1 to about 5 solar radii, so it's pretty close. It was observed with the Arecibo radio telescope, and it was observed over a period of about 30 years, I guess until that telescope collapsed. The variation in the pulse frequency of the pulsar allowed them to determine the orbital period and the geometry of the orbit, and then also to observe the changes in those parameters over time. So they were able to see the orbital decay as gravitational waves radiated energy away from the system. And one could also calculate based on the known, the determined masses and the parameters of the system, what general relativity would predict to be the gravitational wave energy radiated. So the chart on the right shows with the red dots the observations of the change in the periastron, so the closest approach of these in their orbital period. And then as that declines, the dark line shows the prediction from general relativity, and you can see that it is very, very precise. So I've calculated the energy to be radiated through gravitational radiation to be this giant number, 7.35 times 10 to the 24th watts. And just to put that in perspective, the solar system calculated gravitational radiation is about 5,000 watts. So I don't think we could power more than about 50 100-watt bulbs from that. So with that history, I want to say a little bit about the physics behind gravitational radiation. So as most of you know, I'm sure, electromagnetic radiation depends on a dipole oscillation of charges. The dipole is the minimum moment that will produce electromagnetic radiation, but gravitational radiation is a bit different. Dipole oscillation won't produce gravitational waves. It requires a quadrupole or higher moment. And just as an example of what that looks like, if you look at a ring of gravitational masses, they have to oscillate in a way, something like this at a minimum, in order to produce gravitational radiation. And if you were to think of, for example, a spherical mass, it would have to oscillate in a way that would become oblate versus ellipsoid in order to produce a quadrupole moment and and gravitational radiation. Of course, objects orbiting each other also have quadrupole moment, and that is the usual type of system that we are observing at this point. So if we compare the electromagnetic radiation, we know the photon is the carrier of that type of radiation. There is a hypothesized carrier called the graviton for gravitation, which mediates the gravitational field. And you can see from the top entries in these tables that they're actually pretty similar. Both are bosons, they both chargeless, they're massless. But if you look down at the bottom, you can see that their quantum parameters are quite different. So how do gravitational waves propagate? So they actually propagate just like light and any other massless disturbance that has a particle wave duality. And they follow what we call the straightest path in four-dimensional space-time. We call those null geodesics. And those are based on basically the Einstein field equations, but determined by the metric tensor. They travel at the speed of light. And I've put that little caveat there, generally speaking, because in the next point there, as opposed to light, they are actual perturbations in the curvature of space-time. So their path may be influenced by their own disturbance. They also undergo lensing and redshift, just like light waves. So this diagram, which comes from NASA Goddard Space Flight Center, shows all of the different types of gravitational waves that might come from different objects. So if you look down here at the bottom, things that we can detect right now by terrestrial interferometers are things like rotating neutron stars, supernova, and compact binaries that are merging. If we go to, these are things of shorter wave period and higher frequency. If we go to things with longer wavelengths, then these would be things that are happening with supermassive black holes, things that are being captured by them and mergers of them. For these, we're going to need other technologies such as space interferometers. And the pulsar timing can also detect some of these longer waves. As you see, the binary supermassive black hole mergers, basically. There are also hypothesized quantum fluctuations in the early universe that would give rise to gravitational waves of a lot of different frequencies and wavelengths. And to observe these, we probably are going to need both the pulsar timing and a way of analyzing the cosmic microwave background polarization so that we can pick out what might be the influence of these gravitational background radiation. Not been done yet. So we'll get now to how these are detected. So if you were proposing to do this in your backyard, you would need a pretty big backyard. So LIGO right now requires a greater than 4 kilometer square area, which is, as you see there, different areas, 4,000 acres or 1,600 hectares. Needs to be square and needs to be flat. And if you really want to confirm that you're detecting something, you probably need 2 widely separated sites. So you need 2 backyards in 2 different parts of the country. 3 is better if you want to know where the radiation is coming from. You would need some billions of dollars to invest. But if you decide, well, I'll just try what Weber tried, the funding for that was about $200,000 per year in 1969 dollars, which would be around $2 million in current money. And you would need expertise in physics, engineering, statistical analysis, and as we'll see, probably team management, because this requires very large groups of people. The first detection by LIGO, when it's published, had an authorship of almost 1,000 authors. All right, back to Weber. His cylinders were designed to detect gravitational waves with a very specific wavelength range. It was about 1660 hertz. And the reason for that is that they were designed to be resonant at that frequency. And that depended on the dimensions and the speed of sound in aluminum. These were aluminum cylinders. And he did try to isolate them very well. He installed them in a vacuum chamber, and he had acoustic filters that were suspending them, masses on strings, and some rubber pads and so on. So the detection, as you see in the image over here, was through these strain gauges at the center of the cylinder. So as the cylinder would get pumped up by the gravitational waves, the idea was that it would, in resonance, it would vibrate stronger and stronger and then create a signal from these detectors. They were piezoelectric initially. There were some proposed other detectors that were basically quantum devices. I'm not sure these were ever used. And as I said, Weber believed he was detecting gravitational waves. He had one cylinder in Maryland and one at the Argonne National Laboratory in Chicago, and they were connected by telephone lines. There were some questions about how the delays in the telephone lines were analyzed, and also, even more so, his methods of analysis. And most people, I think the physics community, decided that what he was seeing was basically systemic noise. There was another interesting attempt kind of early on. Apollo 17 left a lunar surface gravimeter on the moon. And the idea was that they would measure changes in the gravitational strength on the moon's surface and try to correlate that with gravitational radiation. That was never very successful, although there are still some ideas of trying to do that, and maybe with more advanced technology. So we talk about first and second generation detectors. You could call the Weber resonant bars a first generation detector, but usually when we talk about first generation detectors, we're talking about the initial rollout of the laser interferometers, the LIGO in Washington, Hanford, and Livingston, Louisiana, the Virgo in Italy, and this one called Geo 600 in Germany. The 600 is because the interferometer arms were not 4 kilometers like the LIGO ones, but they were only 600 meters. And that one was kind of important because even though it didn't detect gravitational radiation, it really was a test site for a lot of the technology that was eventually used in these detectors. So they shut down the first generation detectors in 2010 because they still hadn't detected anything, and installed a bunch of upgrades to the so-called advanced or second generation technology. And that was installed both in the US and Italy. In addition, there is another interferometer in Japan called Kagra, and it's sort of called a 2.5 generation detector because it is a little different. It's underground, which is similar to what is proposed for the newer generation, and use some of the more advanced technologies that haven't yet been installed in LIGO and Virgo. We'll talk more about the proposed Einstein telescope and the Cosmic Explorer, which are the proposed new ones. So I wanted to say a little bit about laser interferometry. So basically an interferometer, as you see in the diagram at the top here, is a system whereby you have a light source which is split and goes in perpendicular directions, reflected back by a mirror, and then is detected by a detector of some sort. You probably remember the Michelson-Morley experiment. That one actually wasn't measuring length, but was trying to measure changes in the speed of light as the Earth moved through the luminiferous ether, which was proposed as the medium through which light passed, which supported the passage of light. Of course, the results of that were null. They would take the interferometer and rotate it in different directions and expect if the speed of light changed in one direction, they would see changes in the output. So it's described as the most famous null experiment in physics. And as a result of that, the luminiferous ether essentially evaporated. And we now know, of course, that the speed of light is constant in a medium and vacuum as well as any medium. So for gravitational wave detection, the idea, if you look at the picture at the bottom here, is that the wave is coming through the detector, and as it does, it causes the arm length to change. And so the two lengths in perpendicular directions will change differently. And I'll show a video that shows that in a little more clearly. But you can see that basically there's a laser source. It goes to a beam splitter mirror and then goes out through this 4-kilometer arm to a mirror and is reflected back. Now, it's not reflected just once. The way this is designed is there are about 300 different reflections, which makes this an equivalent length of about 1,200 kilometers instead of just the 4 kilometers, and that makes this much more sensitive. There's also this power recycling mirror, which prevents the laser from the beam splitter from coming back into the source and actually amplifies the power, the effective power, from something like 40 watts of the output, or 25 watts as one source says, to the equivalent of half to 3/4 of a kilowatt. And that also makes the device much more sensitive. So these signal recycling mirrors basically give you this very long length. The other technological advances other than the long length is the advanced mechanical isolation, which we'll talk a little bit about, which is really an engineering marvel. Now, there's more complications than that in terms of the way the beam is detected, in terms of the way the system is isolated, but that's the basic technology. So let me just say a little bit about how it works. So you have two beams of light being combined. So if the two arm lengths are the same, the beams will come back and they will have the same phase. And so they will constructively interfere, which means that the amplitude will add. Okay. As the phase changes, as the arm length changes, the phase changes, and over time, these interfere in such a way that at some point there's destructive interference and you get a null or a dimmer light. So if you look at the two waves coming along to the detector and being added as the arm lengths change, you can see how the amplitude at the detector changes. This is kind of a neat place where they attempt to explain all kinds of stuff, but they explain this as well. So I'm going to play this little video, and this shows a little bit better about how this phase change with the changing arm length as the gravitational wave passes and changes the distances works. Okay. So as the gravitational wave passes, the arm lengths change, and you can see the change in the amplitude. So now it's going to show you the phase of the light. They go reflected by the mirror. Now, of course, it's only showing one reflection. And remember, there are 300 reflections going on in the actual detector. And now the two beams are recombined and they reach the detector. And as that happens, they are either amplified or decreased. You see the beam changing as that changes, and you see the arm lengths changing. And this is what the detector would see. Of course, the detector is much more complicated than just a screen. So this is the way the interferometer works. And of course, as I said, it's a lot more complicated than that. One, eight, go. There we go. All right. I'm going to talk a little bit about the engineering. This is a view of the Livingston, Louisiana installation. You can tell it's Louisiana because it's got lots of green trees. Hanford is a little drier looking, but you can see the two arms, the one going off to the left, and then the one that you see incomplete to the right, and then kind of the main building in the middle. So reviewing the layout, there's a laser. There's this power recycling mirror that gives a more an equivalent, more powerful signal than what's coming out of the laser, a beam splitter, and then the test mass mirrors. So these are the things that are changing their length, the distance between them in response to the gravitational wave. So these are very massive mirrors. These signals come back with the 300 reflections here and come back or reflected back, either going through the beam splitter or reflected through it to the detector. And for Doug Holland's benefit, I put down the type of detector, very low noise radio frequency photodiode. And you can see the frequency or the wavelength of the light. It's 1064 nanometers, at least for this installation. So here's another view of that, and you can see how that is laid out. They have a mid station. They have areas which pump out the vacuum tube in which the light beams travel. We'll talk more about that, which is another engineering achievement. So on the top are these test mass mirrors. They weigh 40 kilograms each, and they cost $2 million each. And they are made out of basically fused silica. The containment on the bottom is a vacuum tube that's 4 kilometers long. This is when it's under construction. So you see the tube. It's also enclosed in this concrete tunnel, which eventually covered all of it. And you can see some of the supports here, which have to compensate for the Earth's curvature, which is about 1 meter over the 4 kilometers. The other really incredible thing is that they have created in all of this installation an ultra-high vacuum to the level of 10 to the 7th molecules per centimeter cube. That sounds like a lot, but that is one of the highest vacuums attainable on the surface of Earth. And that took 40 days to achieve that. So that's a big deal. And if they were to have to open it up and redo it, it would take another 40 days. There are other features related to that, in that they have to heat this up in order to outgas the system. So it's a real engineering challenge. Another one of the engineering challenges was isolating these mirrors from vibration. So one of the ways in which that is done is to make them as pendula. And you can see that there's actually multiple pendula here. So there's a support, there are metal masses, which are the first and second pendula, And then there's a third one, which is called the penultimate mass. This is also a mirror, but it's not the one in the main system. And then there's the test mass, which is the one that is actually reflecting the beam, the main beam. There's also another reaction mass attached to that, which has some technology associated with it. And part of that is also to help actively remove vibration, and they use an electromagnetic system for that. So you can see over here one of the installations, and they actually have seismometers installed here to detect vibrations and supply the active support system with the information needed to counteract those. I've put some of the links down here. The LIGO websites really have a great deal of information if you really want to get into this more. So I just added this slide, but if you really are interested in more information, this guy, Rainer Weiss, was a major driver for this project, and he did a really nice symposium talk, and you can see that on YouTube if you're interested in hearing an insider talk about this. The other way in which in the second generation systems, accuracy is increased is by a technique called quantum squeezing of the photon signal. Basically, that involves a nonlinear optical system that generates entangled photons that end up getting mixed with the main signal. In order to, the purpose of that is to kind of get around the uncertainty principle. So the detection of these waves at this point has reached the point of quantum uncertainty. And the two things that are linked by that are important here are the phase and the amplitude of the signal. So you can enhance your accuracy of one at the sacrifice of the other. So based on the frequency of the noise that you're worried about, you can use one or the other, and they actually use both. I'm probably not going to say any more about that because it's a very complicated topic, and I'm still trying to understand it a little better. But I've put these two images at the bottom to show you the complexity of the optical system that does this quantum squeezing. The one on the left is when it's open for maintenance, and the one on the right, you can see it's illuminated and in action. There's a very nice discussion of this on the LIGO Caltech website, and if you really want to get into there are some interesting articles, this one in Nature Physics. All right, so let's talk about what they've seen. All right, so one of the ways in which the observations are interpreted, well, the main way is looking for the pattern of the signal. So the different types of signals will have different patterns, and these can be calculated by simulations and from general relativity. If you think about, for example, binary system that's spiraling inward and then eventually merging, you can get an idea of what it should look like. So a compact binary and spiral and merger are the main things that LIGO is detecting. Continuous gravitational waves could be generated by spinning neutron stars. They have to have some asymmetry in order to have a quadrupole moment. And these should be of a constant frequency. That might be a little more difficult to determine from our current system. And then there are these so-called stochastic gravitational waves, the ones like the cosmic microwave background. These are being looked for with pulsar timing arrays with variations in these from different pulsars. And then there's some called burst gravitational waves that might be detectable with our interferometers, but from sources that are not totally understood. So this diagram shows the different gravitational wave detections that have been made to that date, to 11/20/23, when that graph was made. And you can see that most of them, the bright dots there are the actual detected masses of the system. And most of them are stellar mass. Black holes are and you can see that there are ones that are neutron stars towards the bottom. The gray circles at the top are the final masses of the systems. The abscissa of this is the distance that is calculated in megaparsecs, but if you look at the top, you can see the z values. So the z values really are not too much more than 1 for our detections. And this is important because the more advanced ones that are proposed can go much farther than that. Okay, so first and second generation detectors, Weber resonant bars, the detection's not confirmed. The laser interferometers we talked about. Did I already had this slide, didn't I? Let's see. Okay. All right, so now I want to show you the signals. And I hope that the audio comes through, but let's give it a try. Let's see. So let me just do a little explanation. There's 2 signals here that are, these are the ones from the initial detection in 2015. The one at the top is from Hanford and the one at the bottom from Livingston, and they're going to run it twice. So the first one is the actual frequency of the signal converted to audio. The second one is altered so that it is more in our hearing range. So you'll hear 2 different ones. Let's see if it works. Can you all hear that okay? Was that audible?
No, Jerry, we don't hear anything.
Oh, that's too bad. So let me see. Well, I would recommend just going to the website and listening to this. Basically, what it sounds like is a low rumble for a little bit and then a chirp. So it's like that. I'll just mimic it. But if you really want to hear it, you can go to the site and listen to that. And I was worried that that might not come through. Go to the next slide.
So one of the comments that Joe Dellinger was just making is that when you initially make the decision to share your slides, there's an option for sharing the sound that may come from the presentation as well.
Is that right? Let's see. So if I stop sharing and reshare, it'll give me an option?
I think it's there. I know it's Teams for sure. Zoom, I think maybe too.
This is Teams.
Yeah, so Joe is saying that he knows there's that option with Teams.
Okay, let me try that. Okay. Looking for it. Oh, include sound. Yeah, it's right at the top. Okay, we'll try it. All right, let's try running it again and see if that works.
Oh, yes.
Okay, great. Thank you.
Oh, yes.
All right. It's good information. Yeah.
I can also tell you that I'm freeze Teams when it hangs too.
Don't jinx us.
Okay. Well, let me show you another video. This one is the merger of two black holes, and the bottom part is a two-dimensional representation of the space-time around these. And you'll see how that changes. The pink is the radiation. So you can see the two orbiting each other and the two gravitational wells related to them. And then as they get closer, there's no sound for this one, so. You can see the wells start to combine. And the orbit getting faster and faster. And this is the moment of combining, which is probably not too well understood. But notice that black dot is kind of still oscillating a little bit, and those pink waves are still coming out until it stabilizes, and then it won't radiate anymore. And you can see the signal that's expected from that. These videos are done by this SXS collaboration, which has done a lot of these nice animations. This one is another one from that same group. And this is what you would see if you were in the vicinity of this event. Notice the ring around it. So what you're seeing around them is basically the gravitational lensing of the background stars.
Wow.
So there is a photon orbit around black holes where photons can basically continue around, but it's unstable. And that's that kind of darker ring you see. And now it's stabilized and merged. So these are simulations that can be done to kind of get an
we
idea.
have a question here. We have a question here. So the question was, what velocity, or say, so what's the period of say rotation that we're seeing there, orbiting that we're seeing right there? Do you have any idea?
I really don't know. I think it's relatively real time. Let me just run it again, and you can see. Well, they didn't show it on this one. On the previous one, there was a signal that showed the orbital frequency, and then you could see as they got closer and closer together, it got higher and higher frequency.
Well, there actually is a note at the top of the slide which indicates that what we're seeing there in the video represents a third of a second in real time.
Yeah.
So those things are orbiting very, very quickly.
Yeah, once they get very close, it becomes very rapid. Yeah. So the oscillation in the signals, I think, is basically the orbital periods as they merge. Let's see.
It really is amazing what a few $1 billion can get you.
Yes. Well, that's an interesting discussion that people have, and it's true with things like the James Webb. You know, what's the value of the expense of this public expense? Yeah, I think a lot of us would be very favorable, but there's certainly people who aren't. So the last thing about detection I wanted to say is something about locating the source. And in order to locate the source, you need more than one detector. You can get an idea from a single detector, but it's not very precise. So the way it's done is by looking at the time of arrival of the signals at different directors that are widely separated. So 3 or more detectors are really required for the best localization. So we have the 2 detectors in the US Virgo in Italy, and Kagra in Japan. So now there are actually 4. And if they all 4 detect a signal, then the localization can be fairly precise. You can see from this diagram, this is just through 2017. So this is not the most advanced detections, but you can see how these were localized on the celestial sphere, different ones. The strength of the signal and polarization pattern also helps triangulate the direction. And if a detector fails to register a signal, it's because that was in the detector's blind spot, which means that the 2 arms are being changed simultaneously the same. And that actually does give you some localization information as well, assuming that it actually would have been detected. All right, so the last part here is future projects. So there are some ground-based telescopes. They are going to continue to improve the technology of the LIGO and Virgo telescopes. There's also this proposed Einstein telescope, and that's one proposed by the European Space Agency. And it is triangular and has several interferometers that are incorporated into a single observatory. Another feature of it is it's underground, and that allows for better isolation from at least surface vibrations. There's also the ability to cryogenic cool the main optics, depending on which frequencies they want to observe. And then these quantum technologies to change the fluctuations in the laser light. There are also improved engineering to mitigate noise. So when is this going to happen? The site selection has not yet happened. And they propose to begin construction in 2026 and go live in 2035. But since they haven't still decided whether to put it in Germany or Italy, probably that isn't going to happen. So as you see the diagram there, there are 2 different frequencies that are used for the lasers, the 1064, which is similar to LIGO, and then a more infrared beam. And there's different optics. So the 1064 uses fused silica optics like the LIGO, but the infrared uses silicone optics. And I didn't realize this, but silicone is actually transparent to infrared light at that frequency, at that wavelength, 1550. So these are designed to basically detect different frequencies of gravitational radiation. And you can see a diagram here of what it might look like. So these are just diagrams to show the different layouts. The high frequency is the one that uses the fused silica, and these are operated at room temperature. The lower frequency, because it's closer to the noise, is cryogenically cooled and uses these silicone optics. And you can see some of the other quantum squeezing types of apparatus in the detection system here. The Einstein telescope is potentially able to detect events going back much farther than these 2nd generation telescopes. As you see here, back to Z100 is what is suggested. Also, it should be capable of seeing more distant objects by their lensing by nearer objects as these move across the field. So this is proposed what might be seen with that type of system. So the US is also proposing new underground telescopes, Cosmic Explorer telescopes, which they are now proposing to have 40 and 20 kilometer interferometer arms. Remember, LIGO is 4 kilometers. So these should be much more sensitive. Um, they've listed a lot of the key science questions that they think these might be able to answer, and you can see things like going back to first stars, the seed black holes that help with galaxy formation, neutron star structure, strong gravity and dark matter and dark energy and quantum gravity, all of those things. This little diagram shows their proposal with what they can build and what they might be able to detect. So if it's just the Cosmic Explorer with the second generation technology, then it is sort of this level. If it is combined with the Einstein telescope, the greener this is, the better it is, basically. Or if they can, and you can see the different configurations, either 20 kilometer or 40 kilometer arms. And if they can combine all three of these, the south one is in Australia, it's proposed to be in Australia, then it's all green, basically. This is all described in a very nice document, which is the Cosmic Explorer Horizon Study. And it is really very readable, so I would recommend that if you want to know more about it. So the final one basically is a space-based telescope, and that's called LISA, for Laser Interferometer Space Antenna. The mission goal is to detect and study waves in the 0.1 millihertz to 1 hertz range, which are much longer waves. It's a triangular constellation of 3 spacecraft, and they are not in orbit around the Earth or even in a Lagrange point, but they're in a heliocentric orbit following Earth. And each side of the triangle is proposed to be 2.5 million kilometers. So again, very much more sensitivity based on the length of the interferometer. The targets are basically merging supermassive black holes, binary stars in our galaxy, some compact stellar mass objects being captured by black holes. This is also proposed for the mid-2030s and should fill a gap in gravitational wave astronomy by the lower frequency signals. And those are not possible to measure from Earth because there's just too much seismic noise. There was a previous mission called LISA Pathfinder in 2015. This was a European Space Agency mission with some NASA contribution that was used to validate the technologies for this system and basically how to suspend the masses and how to do laser interferometry in space and actually how to control these satellites so that they stay very stable with regard to each other. So the next slide shows the configuration, and at the bottom it shows the what would happen to both the orbit of the satellite and, more importantly, the distances between the satellites that are going to be measured by laser interferometry with the passage of gravitational waves. So I just noticed this recent article, which was in Physical Review Letters, which is relevant to that. And these authors are looking at the merger of supermassive black hole binaries. And this would be a situation where you would have perhaps 2 colliding galaxies where the supermassive black holes at the center were either very closely orbiting or going to merge. And this brings up this topic of multi-messenger astronomy. So the idea is you get these gravitational wave signals, then what do you look for with optical or radio telescope, for example? So they want to predict what the signals should be in order to look for those. The gas accretion disks around these supermassive black holes are expected to generate very distinctive features in terms of their spectrum and their light curves. So to be able to correlate these should really help to localize them much better and to get a better idea of what these events actually represent. So back to the spectrum, just as to review, and I want to point out here too that the Weber cylinders have this very narrow bandwidth. And basically, what we were trying to calculate, which was this area, would not even have been within the bandwidth of Weber cylinders as we know now. Going to space-based interferometers will give us the capability of looking at a lot more things, as you can see here. So I just want to end by saying if you're excited by this and interested, you can actually go see this thing. LIGO Livingston has these Science Saturdays, which are the first Saturday of every month. And they have different themes, as you can see for the first three there. And you can go to their website and find out how to get there. I haven't been there, but I really would like to go see it. So with that, I think that's my last slide. I'll see if anyone has any further questions.
Fantastic presentation. So who in the audience has the first question? Dave Haviland is offering his praise.
Dave's already heard it.
Yeah. Dave actually sent us an email today and said, "Man, you guys have to attend this because it is the cat's meow." My words intended, not his. Fantastic. Okay, so who has the first question? Robin. Robin, here you go.
What would be can you hear me?
Yes.
Okay. What would be the effects of a black hole that was feeding on the gravitational waves?
That was feeding on the gravitational waves. That's an interesting question. That certainly could happen. One of the ideas about energy loss from a black hole is that if you perturb the black hole so that it's no longer symmetric, either a static one or a spinning one, then it will emit gravitational radiation itself. So gravitational radiation impinging on a black hole would perturb it and would cause it to, in concert, emit more gravitational radiation. Now, I think this is not enough energy loss to cause them to shrink. If you know about Hawking radiation, you know that the Hawking radiation intensity is dependent on the size of the black hole, the mass. As it gets smaller and smaller, it radiates more of its mass away, and it can basically poof out of existence that way, theoretically. But gravitational radiation of a black hole, I think, is much less, just from its oscillations, because they will return to equilibrium fairly rapidly, I think. I'm speculating a bit here because it's been more than 50 years since I was professionally involved in this area.
I had a question as well, Dr. Campbell. Thank you for the presentation. How long do these gravitational waves keep traveling? Like, one of your graphs actually showed that you can look back all the way to z equals,
right?
Right? Do we still expect those primordial black holes to be still emitting those gravitational waves and still coming through?
Well, some of the events that we saw are back in time quite a ways. So if you think about one of the goals, which is to look at seed black holes that are forming galaxies, these would be ones that are back very close to the era of galaxy formation. So presumably these waves propagate like light does until they hit something, and actually they can go through. They're not really absorbed very well by masses. So I think, we can look back pretty far in time with this.
So from the audience, Bill Spazzeri had a question. It's in chat. It says, so the system must use quantum entanglement to function properly. Now, Bill, which system were you talking about? Because that was at 742.
I'm talking about any of them. He mentioned that that it uses quantum entanglement to measure things or to
This is the,
function.
yeah, I can say a little bit about it, and I can say what I understand about it. So they use nonlinear optics in this quantum squeezing mechanism in order to improve the sensitivity. So part of that involves the creation of entangled photons, which go in different directions. Now, beyond that, I'm not sure I can explain all the details of that system, but it's basically part of the quantum squeezing system, which is part of this second generation newer detection system.
So would it be reasonable to say that this is a confirmation of quantum entanglement because you guys get it to work?
I think most people believe in it. Yes.
Yeah, they believe, but you know, confirmation is handy.
Let me tell you what I read about this system of quantum squeezing, and that is that it was first proposed way back early in at least in the 1970s, and it has been many decades of trial and error to actually accomplish this, and it has been finally accomplished basically about the time that it has being designed for the gravitational wave detectors. So it is not a simple system. And you saw the complexity of that optical system in the pictures.
If you don't mind, I have a second question. I was wondering, early in your presentation, you showed the spectrum with the various things like a neutron collision, etc., neutron star collision. How do you determine when you get the wavelength what kind of event is occurring?
Yeah, that's an important question, and I was a little bit unclear about that when I started looking into this. Basically, what they do is they model these systems and do a simulation and predict what the signal should look like. So when you see a signal, you match the pattern. It's kind of like what we do with brain tumors. You know, we see something under the microscope, we say, yeah, that's what it looks like.
I got you. Okay, thank you.
That's great stuff. Other question? Next question. Oh, there are no further questions. Oh, okay. Matt Pateau has a question.
Hold it. The period. I think I saw that, but you can determine like the mass and the period of the system that caused the wave.
Yes, so that's part of the modeling. So the frequency.
And is that from like the simulation? You can exactly determine.
Right. So you put in the masses and the orbital periods, and you predict what the frequency should look like as the system deteriorates.
Okay. Next question. Next question. Okay, Jerry, I think that we have been totally astounded by you. You have addressed all of the necessary questions. We really appreciate your time with us. This is wonderful presentation, and Dave Haviland was spot on in giving advertisement of the quality of what you've given us today.
Well, I hope it inspires somebody to look further into it.
Absolutely. Thank you so much. Let's give him a hand.
Thank you.